Each of these uranium fuel bundles can produce an extraordinary amount of energy. But before it can generate electricity inside a nuclear reactor, uranium must travel through one of the most tightly controlled industrial processes on Earth. To understand how it happens, we are traveling to northern Saskatchewan, Canada, home to some of the richest uranium deposits ever discovered. Uranium is a naturally occurring metallic element. It was identified in 1789 by the German chemist Martin Heinrich Klaproth. But its enormous energy potential remained unknown for almost 150 years. In 1938, scientists discovered nuclear fission, the process in which the nucleus of a heavy atom splits, releasing energy and additional neutrons. That discovery transformed uranium from an unusual mineral into one of the most concentrated energy sources ever used. Deep beneath the Athabasca Basin lies the McArthur River uranium mine. The deposit is exceptionally rich, but reaching it is difficult because the uranium-bearing rock lies near porous sandstone filled with high-pressure groundwater. Before mining can begin, the surrounding ground must be stabilized. Workers drill long holes around the ore zone and install pipes that circulate extremely cold calcium chloride brine. A refrigeration plant on the surface chills the liquid, which travels underground and absorbs heat from the rock. Over time, the water surrounding the deposit freezes into a solid barrier. This artificial frozen wall performs two essential jobs. It strengthens unstable ground, and it prevents pressurized groundwater from flooding the mining area. Much of the underground equipment is operated remotely. Keeping workers away from the active mining face reduces their exposure to radiation, falling rock, dust, and heavy machinery. To reach the ore, a drilling system first creates a narrow pilot hole through the deposit. A larger cutting head is then pulled back through the pilot hole, enlarging the opening and breaking the ore into manageable pieces. This raise boring method allows the deposit to be mined from protected tunnels above and below the ore body. As the broken material is collected, radiation scanners estimate its uranium concentration. At McArthur River, some ore grades are dramatically higher than the global average. That means a relatively small amount of rock can contain a large quantity of uranium. The ore is delivered to a crushing system where hydraulic equipment breaks it into smaller fragments. It is then ground into fine particles and mixed with water to create a slurry. Every stage is designed to limit contact with the material and prevent its release into the environment. Underground air is ventilated, water is collected and treated, and workers carry instruments that track radiation exposure. At the mill, processed liquids move through closed circuits, while leftover rock and chemical residues are managed in engineered facilities. These precautions matter because uranium presents more than one hazard. It is radioactive, but it is also a toxic heavy metal. The greatest risks during mining and processing often come from inhaling dust, exposure to radon decay products, industrial chemicals, and major dangers of operating deep underground. Engineering therefore protects workers from several hazards at the same time. This slurry is pumped to the surface and transported in specially designed containers to the Key Lake mill, where the uranium is separated from the remaining rock. At the mill, the slurry is transferred through a sealed unloading system. The containers are washed and checked for contamination before leaving the site. The first major processing stage is leaching. The crushed ore is placed in tanks and treated with acid and other chemicals. The uranium dissolves into the liquid, while much of the unwanted rock remains solid. The uranium-bearing solution then passes through a series of separation and purification steps. Chemical reactions remove impurities and concentrate the uranium. Finally, the uranium is precipitated from the solution, dried, and packaged as uranium concentrate, commonly called yellowcake. Despite the name, yellowcake can vary in color. Its main component is usually triuranium octoxide, written chemically as U3O8. From here, the path depends on the type of reactor that will use the fuel. Most light water reactors require uranium to be converted into uranium hexafluoride gas and enriched so that the proportion of uranium-235 rises above its natural level of about 0.7%. Canadian CANDU reactors, however, were designed to use natural uranium. Their heavy water moderator allows them to sustain a chain reaction without requiring the fuel to pass through a commercial enrichment plant. For CANDU fuel, the uranium concentrate is refined and chemically converted into uranium dioxide, or UO2. This material appears as a fine black powder. A sample is tested carefully for its chemistry, purity, density, and particle characteristics. Nuclear fuel must meet extremely strict specifications. Even small variations can affect how the pellets behave under intense heat and radiation inside a reactor. The uranium dioxide powder is blended until its particles form a consistent mixture. It is then fed into powerful presses that compress it into small cylindrical shapes known as green pellets. At this stage, the pellets are solid but still fragile and porous. To strengthen them, they enter a high-temperature furnace for a process called sintering. Inside the furnace, the pellets are heated to well above 1000 degrees Celsius in a controlled atmosphere. The particles bond together, pores shrink, and each pellet becomes a dense ceramic. After cooling, the pellets are ground to extremely precise dimensions. Their diameter must be carefully controlled so they fit correctly inside the fuel tubes while leaving enough space for thermal expansion. A single uranium fuel pellet is only about the size of a fingertip, yet it contains an astonishing amount of potential energy. Depending on the reactor and operating conditions, one pellet can release energy comparable to roughly 1 metric ton of coal. The finished pellets are inspected for cracks, chips, density, and dimensional accuracy. Pellets that do not meet specifications are rejected or recycled. Approved pellets are now ready to become fuel elements. Robotic equipment loads a precise column of uranium dioxide pellets into thin tubes made from a zirconium alloy. Zirconium alloys are used because they resist heat and corrosion while absorbing very few neutrons, allowing the nuclear chain reaction to continue efficiently. Once filled, each tube is sealed at both ends by automated welding equipment. The completed component is called a fuel element. The welds are examined carefully to confirm that the tube is airtight. Fuel elements may also be measured, weighed, and tested for surface contamination. Several individual fuel elements are then arranged in a circular structure and joined together to form a can-do fuel bundle. Depending on the design, a bundle commonly contains 28, 37, or more fuel elements. The finished bundle is compact enough to be handled by specialized machinery, but it contains enough uranium to produce a remarkable amount of electricity during its time in the reactor. Fresh uranium fuel is radioactive, but its radiation level is relatively low compared with fuel that has operated inside a reactor. Workers can handle new bundles using established industrial radiation protection procedures. The completed bundles are inspected one final time, packaged securely, and transported to a nuclear power station. At the plant, the fuel is loaded into horizontal pressure tubes running through the reactor core. Unlike many reactor designs that shut down for refueling, can-do reactors can replace fuel while continuing to operate. Inside the core, the fuel bundles are surrounded by heavy water, which serves as both coolant and moderator. The moderator slows down fast-moving neutrons. Slower neutrons are more likely to strike uranium-235 nuclei and cause them to split. When a uranium-235 nucleus absorbs a neutron, it becomes unstable. It divides into smaller atoms, releases a large amount of heat, and sends out additional neutrons. Those neutrons can strike other uranium nuclei, causing more fissions. This repeating process is called a nuclear chain reaction. The reaction does not occur because uranium is burning like coal. Instead, a tiny portion of the mass inside the atomic nuclei is converted into energy. Reactor control systems regulate the number of neutrons available to continue the reaction. Devices made from neutron-absorbing materials can be inserted or adjusted to reduce reactor power. Independent shutdown systems are designed to stop the chain reaction rapidly if operating conditions move outside safe limits. The heat produced by fission is carried away by pressurized heavy water coolant flowing through the fuel channels. That hot coolant travels to steam generators, where it transfers its heat to a separate supply of ordinary water. The two water systems remain physically separated. The ordinary water boils and becomes high-pressure steam. The steam races through large turbine blades, forcing the turbine shaft to rotate. The turbine is connected to an electrical generator. Inside the generator, rotating magnetic fields move past coils of wire, converting mechanical motion into electrical energy. After passing through the turbine, the steam enters a condenser, where it cools and changes back into liquid water. Pumps return it to the steam generators, and the cycle begins again. A large nuclear generating unit can produce hundreds of megawatts of electricity continuously, supplying power to hundreds of thousands of homes and businesses without burning fossil fuel inside the plant. Over time, the concentration of useful fissile material in each bundle falls, while fission products accumulate. The bundle eventually becomes less efficient and must be removed from the reactor. But used nuclear fuel is very different from fresh fuel. Once irradiated, it contains highly radioactive fission products and produces intense heat through radioactive decay. Remote-controlled fueling machines transfer the used bundles into a water-filled storage pool. The water performs 3 jobs. It cools the fuel, shields workers from radiation, and provides a controlled environment while the radioactivity and heat decline. The bundles typically remain in wet storage for several years. They may later be transferred into heavily engineered dry storage containers made from steel and reinforced concrete. Used fuel remains radioactive for a very long time, so it must be isolated and managed under strict regulatory controls. Countries are developing or operating long-term disposal programs designed to place the material deep underground in stable geological formations. From frozen rock hundreds of meters beneath Saskatchewan to ceramic pellets manufactured with microscopic precision, uranium fuel is the result of mining, chemistry, robotics, metallurgy, and nuclear engineering working together. What begins as ore locked inside ancient stone eventually becomes a compact fuel bundle capable of producing enormous quantities of heat. That heat boils water. The steam turns a turbine. The turbine drives a generator, and through that carefully controlled chain of transformations, energy stored inside the atom becomes electricity delivered to the grid.